Moving on to section 2, we're now going to look at molecular geometry, and we're going to contrast that with electron domain geometry because there is a difference between the two. So let's take a look and review of what electron domain geometry was. Electron domain geometry was based on the electron domains, which remember are just simply areas of space where electrons are occupied. So electron domain geometry is based on electron domains, which means they could either be bonds or lone pairs. Basically, the electron domain geometry just simply looks at all the electrons. It doesn't really pay attention to, is it a bond? Is it a lone pair? It doesn't matter. As long as it's a region of space where electrons are occupied, it's an electron domain, which will affect the geometry. So for example, in this particular molecule that you see here to the right, there are 1, 2, 3, 4 electron domains that are around this central atom. One of them happens to be a lone pair, and the other 3 happen to be atoms, but they're all electron domains. And so what did we call the electron domain geometry for 4 domains? It's tetrahedral, right? So that would be the electron domain geometry. But molecular geometry is different because molecular geometry is only based on atoms. In other words, it only is based on the bonds that are there. Now, obviously, there's still the lone pairs, right? Because the lone pair is a region of space that has electrons. So it is important for the geometry. But when you're looking at the molecular geometry, the molecule's geometry or shape of the molecule, we're only looking at the actual atoms. So in the example that we saw above here, if you were to take, and let me get rid of some of this stuff. If you were to take a look at this, but just focus on the 3 atoms that are bonded, you'd be left with this shape. This shape right here is the molecular shape, and we would actually call it trigonal pyramid. Why do we call it trigonal pyramid? Well, trigonal because there are 3 atoms that are bonded to it, and pyramid because if you take a look at that shape that it kind of draws, it kind of looks like a little pyramid, right? There's always reasons behind why we call it the certain shape that it is. But that's the difference between the molecular geometry and the electron domain geometry. So the electron domain geometry is what sets us up for then being able to solve the molecular geometry. So you're going to see that when we look at the order of how you figure things out, you need to first figure out electron domain geometry before you can do molecular. Okay? Now this is a cheat sheet that you can use, but like I said, if you were to go to the additional course materials in Canvas, there's actually a printed geometry sheet that you can use. I recommend using that. It looks a little different than this one, but it's the same information. Otherwise, if you want to use this one here in the notes, notice that you have your number of electron domains, and then when you know your number of electron domains, you just ask yourself, okay, of those electron domains, how many of them are lone pairs? Is it 0 lone pairs? Do I have 1, 2, 3, or 4? So, and then you just navigate to it, and it'll tell you what geometry is there. Notice that when you have 0 lone pairs, when there's no lone pairs of electrons, the molecular geometry is actually the same as the electron domain geometry. So you see here, you've got your 5. It's only when you start to have lone pairs that you start to have different names, such as we'll see bent, or trigonal pyramid, or seesaw, things like that, right? So it's when lone pairs come into play. Okay, before we get started with some examples, one quick note about lone pairs since we've been mentioning it. When you have a molecule that has lone pairs of electrons on the central atom, when we talk about bond angles, the bond angles are actually going to be a little different because lone pairs actually repel more. And so because they're not bonded, they experience less nuclear attraction. All we need to know is when there's lone pairs on the central atom, those lone pairs are going to repel a little bit more. So what does that look like? So if we were to take a look at a regular trigonoplanar molecule, for example. Remember, trigonoplanar has the 3 atoms, okay, and it's 120 degrees. But what instead of being 3 atoms, what if 2 of them were atoms, and then that 3rd electron domain was a lone pair? Well, that lone pair ends up pushing down the other 2 atoms, right? So this lone pair here ends up repelling more, and so it's going to squish those atoms a little bit closer together. And so what you end up getting is that these 2 atoms here are actually closer to each other. We would say it's less than 120, right? And so that's what you would need to do. Now, a lot of times students struggle with knowing which way the alligator eats. So I always recommend just write the words less than, and then you should be good to go. Right? So that's how lone pairs will affect the bond angle. Okay, with that being said, here's how you figure out molecular geometry. First things first, this is super important. You need to draw the Lewis dot structure. The reason why that's important is because if you don't draw the Lewis dot structure, how would you know, just looking at a formula, that there was a lone pair? For example, okay, and we'll see this in just a moment, but for example, water is H2O. Now, how would you know that there were lone pairs on the oxygen? You wouldn't unless you actually drew the Lewis dot structure, right? It's only after you draw the Lewis dot structure that you notice, oh yeah, there's lone pairs on the central. So that's important. You have to start out with a Lewis dot structure. The next thing you're going to do is you're going to count the number of electron domains. We did this in example 1. The third thing is you'll figure out the electron domain geometry based on how many domains. And then you'll ask yourself, okay, of those electron domains, how many are bonds, how many are lone pairs, to figure out what the molecular geometry is. And so you can actually see a visual of that process. So for example, if we were looking at NH3, we would first draw the Lewis dot, then figure out what its electron domain geometry is, and then finally figure out what its molecular geometry is. And so we're going to do that example in example 2. So in example 2, it says consider the following 3 compounds. We have CH4, NH3, and H2O, right? So I know you know how to do this, and so real quickly, what I'm going to do is I'm going to get those Lewis dot structures all drawn for us. There we go. So we've got our 3 Lewis dot structures there. So now that we have our 3 Lewis dot structures, the first thing we're going to ask about each and every single one of these is what are their electron domain geometries. So we need to count how many electron domains there are. So in methane, there are 4 electron domains, which means the electron domain geometry, and I'm going to write that as EDG, is going to be tetrahedral. What about NH3? How many electron domains are there? 1, 2, 3, 4. So ammonia, NH3, would also have an electron domain geometry of tetrahedral because there's 4 electron domains. And finally, water also has 4 electron domains. So the one thing that all 3 of these molecules have in common is they all have the same electron domain geometry because they all have 4 electron domains, tetrahedral. So if we think about it in terms of a general structure here, okay, they're all going to have the same general shape of the tetrahedral molecule, right? That ceiling fan molecule. Okay, but to figure out the molecular geometries, we now need to figure out, okay, of those electron domains, how many of them are bonds and how many of them are lone pairs. Okay, so taking a look at this first one, of those 4 electron domains, how many of them are lone pairs? Well, 0. There aren't any lone pairs. Each electron domain is an actual bond to an atom. So remember, when that happens, the molecular geometry is the exact same as the electron domain geometry. It would still have the tetrahedral shape. If I take a look at the second one, of the 4 domains, one of them is a lone pair. The others are bonds. So if we take a look at our chart, the molecular geometry for that would end up being trigonal pyramidal. Or it's okay to just say trigonal pyramid. That's fine with me. Alright, so taking a look over here, that would basically be erasing that part, and we're left with this pyramid shape, right? And then finally, for the last one, water, of those 4 electron domains, 2 of them are lone pairs. And so that actually ends up giving us a molecular geometry that is bent. And if you were to visualize that, that's like saying, okay, remove another one of these atoms, notice what shape you end up having. You end up having a bent shape. So they all had the same number of electron domains, but their molecular geometry is differing because they have different numbers of lone pairs. Finally, what are the bond angles? Well, the bond angle for tetrahedral, remember, is 109.5 degrees. So this is 109.5 degrees, this is 109.5 degrees, and this is 109.5 degrees. The bond angle will come from your electron domain geometry, and they're all tetrahedral. But we have a lone pair here, and we have lone pairs here, which are actually going to end up squishing our atoms. So for these two right here, it would actually be less than 109.5. And so to sum up, on this screen right here, we actually have the work all done for us. We have our CH4, our NH3, and our H2O. Notice that all three of them have that same skeletal tetrahedral structure, right? But because each one has different number of lone pairs, this is where we actually end up getting our different shapes. The tetrahedral for CH4, the trigonal pyramid for NH3, and the bent shape for water. Notice the bond angles for ammonia and water are less than 109.5. Specifically, ammonia is 107, water is about 104.5. You don't need to know that. That's just giving it details. You just have to know that it's less than 109.5. All right, so let's take a look at some examples. So we have two examples here. We want to figure out what are their geometries and what are the bond angles. So we're going to figure out what's the electron domain geometry, what's the molecular geometry, and then what's the bond angle. So the first thing I'm going to do, I know you know how to do this by yourself, so actually for practice, if you want, draw the Lewis dot structure. That's what I'm going to do in just a moment. So if you want to do the Lewis dot on your own, pause the video and then hit play and you'll see the Lewis dot. Alright, so we have our Lewis dot structures. Notice for SO2, there's actually two ways you could have drawn it, and I put both of them there for a reason. Some of you may have drawn it where you have sulfur with an expanded octet having the two double bonds, which actually, by the way, is the more stable one. But some of you may have also just drawn it with the one double bond, and that's fine too. Both are acceptable. Both will get you the right answer, and that's actually why I wanted to show you that. And then over here real quick for XeF4, notice it doesn't matter where you put the lone pairs on the xenon. So just hopefully you had those two lone pairs on xenon. That's allowed because it can have an expanded octet, right? Okay, so to figure out the electron domain geometry of SO2, first of all, how many electron domains do you have? Well, whether you were looking at this one on to the left or this one over here to the right, it doesn't matter. They both have 3 electron domains, which remember, that is a trigonal planar electron domain geometry, meaning that you're going to have this central atom that has 3 electron domains jutting off of it in the plane of the board. Now, of those 3 electron domains, 2 of them are bonded to oxygen, 1 is a lone pair. So if you take a look at that, okay, if I get rid of that, that's my lone pair, right? And I want to ignore that. What am I left with? I'm left with a bent shape. Now, what's the bond angle for trigonal planar? Bond angle for trigonal planar is 120 degrees. But since I have a lone pair up here, that lone pair actually repels. So these two atoms will end up getting closer together. So I'm going to make that less than. I will not require you to do this unless I ask for it explicitly, but it is sometimes a good idea, once you know the shape, to redraw the Lewis dot to actually represent the shape of the structure. So I would redraw it as bent. In later chemistry courses, they may require you to do that. Over here with xenon tetrafluoride, how many electron domains do we have? We have the 4 bonds to fluorine, and we have the 2 lone pairs. So we have 6 electron domains, which means our electron domain geometry is octahedral. Now of those 6, 4 of them are bonds, 2 of them are lone pairs. Okay, so if we kind of think about our general structure here, let me draw it real quick. Okay, so this is the octahedral shape. So those are our 6 electron domains, but 2 of them are lone pairs, and specifically it'll be the ones that are on top right there. So what are you left with? Well, you're left with this flat square, right? So that's why we call this molecular geometry square planar. Now, what is the bond angle for octahedral? Octahedral is bond angles of 90 degrees. Now, there are electrons, right? There are lone pairs on the central, but this is an exception. Since you have a lone pair on the top and a lone pair exactly on the bottom, they are sandwiched right on top of each other, geometrically speaking. Their effect cancels each other out because the lone pair on top would want to push everything down, and the lone pair on the bottom would want to push everything up. So it actually cancels each other out. So this is an exception that even though there are lone pairs, since they cancel, it's going to be exactly 90 degrees. We're going to keep moving on with example 3 in the next video.